Tungsten is one of the most important materials being considered for future nuclear fusion reactors. Its unusually high melting point, resistance to erosion, and ability to tolerate intense heat make it particularly attractive for plasma-facing components, the parts of a reactor that sit closest to the extremely hot fusion plasma. ITER, for example, uses tungsten armor on its divertor targets, where surface heat loads are expected to reach roughly 10 megawatts per square meter during steady operation and even higher levels during some transient events. Yet withstanding the heat is only part of the challenge. Tungsten must also endure a continuous stream of energetic particles, especially neutrons produced by fusion reactions. A new study by Jesper Bigmastar and colleagues suggests that the atomic-scale radiation alterations produced in tungsten can behave differently from what conventional models predict. Published in Physical Review Letters in July 2026, the research used extremely large molecular dynamic simulations to investigate how tungsten responds when individual atoms receive energies ranging from only 40 electron volts to as much as 2 megaelectron volts. The researchers identified 4 distinct regimes of primary radiation impact, including an important region where the number of remaining defects increases faster with energy than established models would suggest. Why fusion neutrons alter tungsten? Most proposed power-producing fusion systems would use deuterium and tritium as fuel. Their fusion reaction releases a neutron carrying about 14.1 MeV of energy. Because neutrons have no electrical charge, they can travel into reactor materials and collide directly with atomic nuclei. In tungsten, such a collision can transfer enough energy to displace an atom out of its normal position in the crystal lattice. That displaced atom, called a primary displaced atom or PDA, can then impact additional atoms, producing a rapidly expanding collision cascade. The new study calculates that fusion neutrons can generate tungsten recoils with energies up to approximately 300 keV. After the cascade cools, some displaced atoms return to normal lattice positions, but others remain as defects. A vacancy is created where an atom is missing, while a self-interstitial occurs when a displaced tungsten atom occupies an abnormal position within the lattice. Together, a vacancy and corresponding interstitial form what researchers call a Frenkel pair. These defects can also combine into clusters, voids, and dislocation loops. Understanding their initial production is important, because primary structural wear provides the starting microstructure from which longer-term irradiation effects develop. Modern models such as the thermal recombination corrected displacements per atom, or ARC-DPA, model attempt to account for the substantial recombination that occurs during these cascades. A billion-atom simulation. Reproducing such events atom by atom is computationally difficult because high-energy collision cascades can extend through enormous numbers of atoms while unfolding on extremely short timescales. Bigmastar's team addressed this problem using a machine-learned interatomic potential combined with molecular dynamics calculations accelerated on graphics processors. Their largest simulations contained more than 1 billion tungsten atoms in a cube approximately 255 nanometers across. The calculations were carried out using the LUMI supercomputer. The researchers simulated recoil energies across 6 orders of magnitude, from 40 electron volts to 2 MeV. The highest energy simulations therefore exceeded the maximum recoil energy expected from fusion neutrons and entered the range relevant to heavy ion experiments commonly used to imitate neutron irradiation. For each simulated cascade, the researchers tracked vacancies, self-interstitial atoms, dislocations, and defect clusters. At 2 MeV pKa energy losses to electronic excitation reduced the average energy actually available for atomic alteration to about 1.2 MeV. 4 different radiation regimes. The most important result was that tungsten did not follow one simple relationship between recoil energy and remaining defects. Instead, 4 regimes emerged. The first occurs near tungsten's threshold displacement energies, where recoils often fail to create a permanent defect. The second involves conventional, relatively compact collision cascades. In this region, defect production increases sublinearly with energy and agrees reasonably well with the ARC-DPA model. The third regime begins at approximately 20 to 30 keV, and is the most important for the claim that tungsten could experience more primary wear than previously expected. As recoil energy rises, a single cascade begins splitting into smaller subcascades. However, these subcascades remain close enough to interact. Their transient heat spikes and pressure waves overlap, promoting the creation of large vacancy clusters and dislocation loops. Instead of wear increasing proportionally, or less than proportionally with energy, defect production becomes superlinear. In other words, increasing the energy produces a disproportionately large increase in permanent defects. The simulations show especially clear examples of this behavior around 200 keV, which lies inside the range relevant to tungsten recoils created by fusion neutrons. This is why the result matters for fusion material modeling. A simplified model that assumes a smoother or purely linear relationship can miss the enhanced defect production associated with interacting subcascades. Earlier studies had already suggested that tungsten could exhibit such upward deviation, but the new simulations followed the process over a far larger energy range and revealed how it eventually ends. The surprising 300 keV transition. Above roughly 300 keV, the calculations revealed a fourth regime. At these energies, the individual subcascades become sufficiently separated that they no longer interact strongly. Defect production therefore returns to an approximately linear trend. Significantly, the transition occurs near the maximum 300 keV recoil energy that a 14.1 MeV fusion neutron can transfer to a tungsten atom. The researchers describe this coincidence as useful because heavy ion irradiation experiments often produce tungsten recoils well above the fusion-relevant energy range. Once the cascades are separated, their effects can potentially be related back to fusion-relevant conditions through the newly quantified linear scaling. The study also found that defect clustering changes strongly across these regimes. At lower energies, approximately half of the self-interstitial atoms but only about 15 to 20% of vacancies were clustered. At high energies, almost all interstitials and roughly 60% of vacancies belong to clusters. The largest frequently produced clusters contained around 1,000 vacancies or interstitials and measured roughly 4 to 10 nanometers across, depending on their structure. These results are broadly consistent with earlier experimental observations of nanometer-scale dislocation loops in ion-irradiated tungsten. What this means for fusion reactors. The research does not demonstrate that a tungsten reactor wall will fail sooner by a specific percentage, nor does it directly calculate the lifetime of an ITER or commercial fusion component. The simulations describe primary wear following individual atomic recoils over roughly tens of picoseconds in initially pristine tungsten. Real reactor materials experience billions of repeated irradiation events together with high temperatures, stresses, helium and hydrogen implantation, transmutation, grain boundaries, pre-existing defects, and continuous microstructural evolution. Bigmaster and colleagues explicitly identify longer irradiation timescales and realistic microstructures as subjects requiring further investigation. What the study changes is the starting point for those larger-scale predictions. It provides evidence that tungsten passes through a superlinear defect production regime precisely within energies relevant to fusion neutron wear. Models of long-term material degradation therefore need to represent that atomic-scale behavior correctly rather than assuming an overly simple dependence on recoil energy. At the same time, the newly discovered linear regime above approximately 300 keV may make it easier to interpret high-energy ion experiments used as substitutes for unavailable fusion-intensity neutron sources. Tungsten remains one of the leading plasma-facing materials for future fusion systems. The study does not overturn that position. Instead, it illustrates how difficult the materials problem remains. A metal can possess the highest melting point of any metal and still accumulate microscopic structural changes under neutron exposure. If fusion power plants are to operate reliably for long periods, understanding how these atomic defects form, cluster, move and evolve will be as important as understanding how reactor walls survive the extraordinary heat of the plasma.